Hello everybody, welcome to today's lecture. We will be continuing to discuss material balances for single unit operations with a single reaction. Until now we have solved example problems where the chemistry of the reaction happening has actually been explicitly given in the form of a traditional chemical equation. So we have used the stoichiometry directly. Today we will see an example problem where the reaction is not given explicitly, however the information regarding the stoichiometry can be obtained based on the different information that has been given in the problem. So here is the example problem. You want to design a hollow fiber membrane device to be used as an artificial liver to bridge a patient from liver failure to transplantation. Determine the concentration of bilirubin with a molecular weight of 474 Dalton and albumin with a molecular weight of 66 kilodalton in the filtrate flowing out of the device into the patient. Blood flows into the device at 150 ml per minute and filtrate flows out at 220 ml per minute. The volume of the device is 500 milliliters. The entering bilirubin concentration is 10 micrograms per ml and its fractional conversion in the device is 83.4%. The entering serum albumin concentration is 2 micrograms per ml and its rate of production by the hepatocytes is in the device is 5 grams per day. You can assume that the density of blood is 1 gram per ml. So this is an artificial liver device. So you can look at the device and try to understand how this system is. So you actually have multiple tubes which are present inside the hollow membrane. So each of these tubes are the ones where you have the blood flowing. So inside this tube these tubes you would have the blood flowing and there are cultured cells in the gaps between this. So these gaps are actually filled with cultured cells which are the hepatocytes in this case. Hepatocytes are nothing but liver cells. So these liver cells can process the blood to make sure that the blood becomes free of contaminants and toxins. So what is being done here is instead of having your natural liver which would regularly perform this, you are having this device which is an extracorporeal device. So blood from the patient is taken and it is allowed to flow through these hollow fiber membranes. It flows into these tubes which are given here. While it is flowing through these tubes, because there is a fiber which is surrounding these tubes, some of the filtrate will get filtered and enter into the space between these tubes where it gets acted upon by the cultured cells, thereby purifying the blood, and this filtrate which comes out from the extracapillary outlet is mixed with the intraluminal blood to finally be sent back into the patient as purified blood. Now to understand this in a simpler block diagram, we can draw it this way. So we have blood which is coming from the patient at 150 ml per minute and this enters into the artificial liver device and we have two outlets. The first one is the filtrate which is leaving at 20 ml per minute and you have the other outlet which is the intraluminal blood leaving the artificial liver device. So this blood and the filtrate are mixed together to finally form the blood which is entering into the patient. Now here for this problem the chemical reaction which is happening is not been explicitly given. However, we can use the data given for generation and consumption and calculate material balances. So let us start solving this problem. Just like any material balance problem, we first need to identify the basis. Based on the information given in the problem, the basis would be 150 ml per minute of blood entering the system. So we write down the basis as 150 ml per minute of blood which is entering the system. So this is also equal to 150 grams per minute of blood because it has been given that the density of blood is 1 gram per ml. So now for performing the calculations we have to make certain assumptions. The first assumption we make would be steady state. So this is a standard assumption which we make for all material balance problems till this point, and in addition to this we should also make a few other assumptions which are specific for this problem. We need to assume that albumin and bilirubin are only leaving through the filtrate. We are going to assume none of the albumin and bilirubin are going to be leaving through the intraluminal blood which is leaving the extracorporeal device. So, bilirubin and albumin come out only in the filtrate. So, this is the second assumption we make. So, the third assumption we would be making is, other than this, no other cells or large molecules would be leaving through the filtrate. No cells or large molecules in the filtrate. These assumptions are essential for performing our calculations. So, now that we have the system and we have all the information, we can start writing the balances. The total balance would not be of much value to start with. So, because of that we will start with the component balances. So, in this case we will first start with the bilirubin balance. The bilirubin balance would be mass of bilirubin entering through the bloodstream 1, which we can call as M1 bilirubin, and mass of bilirubin which is leaving the system would be only through the filtrate based on our assumption. So, we will have this as M2 bilirubin, and in addition to this, bilirubin is being consumed in the system when this liquid is being exposed to the hepatocytes. So, we would have a material balance as input minus output plus generation minus consumption equals accumulation. At steady state there is no accumulation. So, this bilirubin is not being generated by the system. So, generation goes to 0. We know that there is going to be a consumption term, there is an input term and an output term. So, based on this we can write the bilirubin balance as M1 bilirubin would be equal to M2 bilirubin plus consumption of bilirubin. So, it has been told that the conversion of bilirubin in the device is 83.4%. So, this is the percentage conversion. So, conversion is defined as amount of bilirubin consumed by amount of bilirubin fed. So, using this we can calculate the consumption of bilirubin. So, this would be, conversion is 0.834 would be equal to amount of bilirubin which is entering minus amount of bilirubin which is leaving, which is basically the amount of bilirubin consumed, divided by the amount of bilirubin which is entering, which is M1 bilirubin. So, using this we can calculate M2 bilirubin, because we know the value for M1 bilirubin to be 150 ml times 10 micrograms per ml, which is the concentration of bilirubin in the blood entering. So, this is 1500 micrograms of bilirubin is entering the system. So, substituting this value there, we can calculate the amount of bilirubin which is leaving the system as 249 micrograms per minute. So, this would be ml per minute, I am sorry, this would be ml per minute and this is microgram per minute. And with this we have the amount of bilirubin which is leaving the system. So, now that we have the amount of bilirubin, we have to calculate the concentration of bilirubin which has been coming out through the filtrate and the concentration of bilirubin in the blood which is entering the patient. So, we know that 20 ml per minute of filtrate is leaving the system, which means the rest 130 ml would be coming out through the bloodstream. So, the total amount of blood which would be entering the patient would still be the same. Assuming the total mass balance, we would have to assume the total blood leaving the system would still be 150 grams per minute, which is 150 ml per minute. So, based on that we can calculate the concentration of bilirubin in filtrate as 249 micrograms per minute divided by 20 ml per minute, giving you a concentration of 12.45 micrograms per ml. So, the concentration of bilirubin which is entering the patient, in blood entering the patient, would be the same amount, 249 micrograms per minute divided by 150 ml per minute, giving you a concentration of 1.66 micrograms per ml. So, this would be the concentration of bilirubin which is entering the patient. Now, we need to perform these calculations for estimating the concentration of albumin. For this, we would have to perform albumin balance. Let us start with the albumin balance here. Albumin balance would again have the same terms, which would be input minus output plus generation minus consumption equals accumulation. At steady state, there is going to be no accumulation. Albumin is not consumed in the reaction, but it is being generated at a rate of 5 grams per day. So, there is no consumption. However, there will be an output and a generation term, and there is also going to be an input term. Okay. So, with that, to calculate the output of albumin, we will need to know the input plus generation terms. The input term, we will call this as M1 albumin. M1 albumin is known to be 2 micrograms per ml concentration coming in. So, 150 ml per minute times 2 micrograms per ml gives you a concentration, gives you an amount as 300 micrograms per minute. So, 300 micrograms per minute of albumin is entering into the artificial liver device. So, the generation term can be calculated as 5 grams per day given to you in the problem. This needs to be converted to micrograms per minute. So, how do we do that? So, we have to convert the generation term which has been given in 5 grams per day to micrograms per minute. So, how do we do that? 5 grams per day needs to be converted to micrograms per minute. So, 1 gram contains 10 power 6 micrograms, 10 power 6 micrograms per gram times 1 day basically contains 24 hours and 1 hour contains 60 minutes. So, cancelling out the days, cancelling out the grams and the hours, we end up with micrograms per minute, and when we calculate this, the value would be generation equals 3.472 times 10 power 3 micrograms per minute. So, now we have the generation and the input term. So, we can calculate the output term in the filtrate, which we would call as M2 dot albumin. So, M2 dot albumin would be equal to input plus generation, which is 300 plus 3.472 times 10 power 3, giving you a value of 3.772 times 10 power 3 micrograms per minute. So, now just like how we calculated the concentration of bilirubin in the filtrate and in the blood entering the patient, we will have to calculate the concentration of albumin in the filtrate and the albumin entering into the blood entering into the patient. So, concentration in filtrate, so this is albumin concentration in the filtrate would be 3.772 times 10 power 3 divided by 20, giving you a value of 188.6 micrograms per ml. Albumin concentration in blood entering the patient, would be 3.772 times 10 power 3 divided by 150, which is equal to 25.15 micrograms per ml. So, with this we have calculated all the concentrations that have been asked for. As you saw here, we have not used the traditional stoichiometric equations. However, the consumption and generation terms which were given in terms of fractional conversion and generation of some protein in grams per day have been used to perform the material balances. So, this is another type of a problem which you would face in many cases, especially in biological reactions, where reactions are not very straightforward, where you do not have the stoichiometry. However, you might have information on what is being produced at what rate and what is being consumed at what rate. So, using this we can still perform material balance calculations as we have demonstrated here. So, with this we will come to a closure for performing material balances for single unit systems with a single reaction happening. So, we will move on to performing material balances for systems which have multiple reactions. If you remember, when we discussed the fundamentals for in reaction systems, we talked about terminologies associated with multi reaction processes. We will try to apply them to perform material balances in the next lecture. Thank you.